In this part, we are going to analyze the factors other than reactant concentration which affect chemical kinetics, that is, reaction rate. It has been seen that this rate constant is not constant for all reaction conditions. The rate constant has been found to increase with temperature. This temperature dependence of rate constant was explained by Swedish Arrhenius in the following equation called Arrhenius equation, which was proposed by Dutch chemist Van 't Hoff. See that the rate constant depend on absolute temperature, activation energy, and the frequency factor. First, let me explain energy of activation. Chemical reactions involve some chemical change which needs restructuring of chemical bonds, which in turn need energy. In this process, the reactant form very short-lived reaction intermediate called activated complex or transition stage. It is unstable and is of higher energy than the reacting molecules. After this, there is formation of new bonds and the product is formed, releasing energy, and the energy fall. This difference is called the activation energy, and this difference is called the heat of reaction. Heat of reaction, as we all know, is negative for exothermic reactions and positive for endothermic reactions. For every reaction to take place, the reactant molecules must cross this energy barrier. Otherwise, reaction will not proceed. The reaction which have less activation energy is easier to take place and will proceed rapidly. The reaction having high activation energy will proceed slowly. The activation energy may be calculated from the Arrhenius equation like this. We plot a curve ln k versus 1 by t, and the slope of the curve gives minus activation energy divided by r, from where energy of activation may be calculated. Otherwise, if we have two values of k at two different temperatures, then we may calculate activation energy like this. The temperature also play a part. This can be understood by the curve, which is the energy distribution curve prepared by Boltzmann and Maxwell, which show the fraction of molecules having a particular kinetic energy E. The curve showed that this energy is with maximum reactant molecules and is called the most probable energy. This is the energy of activation, and this fraction of reactant molecules exceed energy of activation and form product while others do not. What happens if we increase temperature? We see that fraction of molecules exceeding energy of activation increase. Now more molecules exceed energy of activation and form product. Note that temperature doesn't lower the energy of activation but only help more reactant molecules crossing the energy barrier. The collision theory. The collision theory developed by Mark Trotz and William Lewis in 1916 is based on kinetic theory of gases, where the reactant molecules are thought of as spheres. Reaction occur when collision take place. However, all the collisions do not lead to successful product formation. Effective collisions are those where the reactant molecules cross a certain energy barrier, that is, energy of activation. The colliding molecules also should be properly oriented. When two NO2 molecules collide to form N2O4, this type of collision is effective, but this type of collision is not. According to collision theory, the rate is equal to this value. This is the collision frequency Z. This is the energy factor, which is called the Boltzmann factor, which corresponds to the fraction of reacting molecules which have kinetic energy equal or greater than the activation energy. And this is the probability factor P, depending on steric conditions to judge proper orientation. Role of catalysts and enzymes. A catalyst helps the reaction take place more effectively and speedily by following a completely different path. The reactants react with catalyst and then breaks up to give product. Due to engagement with catalyst molecule, the bond restructuring of reactant molecules become easier, lowering the activation energy. Therefore, catalysts speed up chemical reactions by lowering activation energy. Enzymes are complex nitrogenous organic compounds and act as even more effective catalysts and are termed as biochemical catalysts. Enzymes are very specific and is suitable only for a given reaction. Enzymes are used in chemical reactions in colloidal form, which has cavities of characteristic shape and active groups like NH2, COOH, and OH, etc. These cavities can only accommodate specific reactants called substrate and forms enzyme substrate complex intermediate. This is lock and key mechanism. Finally, the product is formed.